Hi, and welcome back to Book Club. So we're going through applied numerical methods, and again, this doesn't have to be with Python. You can take your best programming language pick. In fact, so many of these books cover mostly of the same topics. So what I'm really kind of doing here is giving you this introduction through really the digitization and discretization of computers and how you solve real problems on a computer. And I don't care if you're just like using Excel to solve something, or you're actually cranking out hard with a MATLAB or a Python or some sort of advanced code that you're using behind the scenes. And so today, what we're going to dig into today is eigenvalues. Okay, and eigenvalues is it's one of these terms that means nothing to you if you haven't heard it before. It's also, of course, it's named after somebody. And the most unfortunate thing is unless this rings a bell, the easiest thing to think about this is like natural mode vibrations. So if you ever heard a ceiling fan spin up, and it sort of spins up, and you kind of get this speed where it really buzzes at you, and then kind of settles into a higher speed. It's this natural frequency. Okay, if you've ever plucked a guitar, what you actually input into that string is this broad spectrum of frequencies, and then the thing that actually, everything else kind of cancels away except for these harmonics, and that's what a string is. So same thing with the piano. So all of this stuff, I'm going to do my best job. Most of these textbooks either get too down into the math, or their examples are too far removed from reality. So I'm going to do my best here to sort of match both. We'll have a little bit of math, we'll have a little bit of examples, because then this is actually one of the most computation intensive things we can do that has very use. So I'll kind of come back to some real world examples of it. Okay, but just as a reminder, we're started getting used to thinking about this language. So if this is a matrix and then a list of unknowns x equal to some right hand side, that's one of the things I do like about this book. Okay, is referring to this as the interactions. This is the stimuli, and this is sort of the response. Okay, the response. And so an eigenvalue problem is simply asking, not B as a stimuli, but an eigenvalue problem is asking this. And this is just a number, and this can be a complex number, but it's a singleton number. So this is saying that my response is some multiple of my stimuli. That's what you're solving for. Now, in this case, both the lambda is unknown as well as the x. And so it's sort of this combined problem. And again, what we're looking for here under this characteristic is when is my stimuli related to my response? Okay, and it's actually kind of back to that guitar plucking, things like that. And so this can also be recast into our standard form. You could say this is A minus lambda, and then I is the identity matrix, right? Just ones along the diagonal. X is equal to 0, and this might be the way that we frame it. Okay, so if you've ever taken, if you've seen this before, eigenvalues in a math class, we would actually look at this matrix, and I'll write it out in a different color. But we would actually say matrix A, and take a look at this. It would be A11, A12, A13, A21, A22, A23. And I'll just do a three-dimensional one. Again, this can be much bigger than 3 dimensions. 3-1, A32, A33. And so what we're actually solving is this minus lambda on the diagonals. Okay, when is that times x equal to 0? Okay, and there's a thing called Cramer's rule that is sort of the direct way of solving this, and it's just an algorithm. It's actually very related to what we did before in the past with kind of Gauss-Seidel. But you can actually go through this, and you could turn the crank if n was equal to 2 or n was equal to 3. It's not unreasonable for a human to go turn the crank. Okay, especially if n is equal to 2, this is only a quadratic, and we actually know how to do quadratics. You sort of learned that probably in 5th grade, right? The b squared minus square root of 4ac over 2a. So we can solve this. Cubic gets a little bit harder, and then of course past that, we're now sort of squarely into the realm of the computer. But the thing that is important about this, so even if I added up the level of operations I'm doing here, and again, I have to both solve for lambda, and then given lambda, I would do this to solve for lambda, and then given a lambda, I would come back and solve for x. Right? what you see is this takes n cubed per eigenvalue. Well, maybe you don't see that, but this is the result. Okay, so this is a very, very expensive calculation. Okay, so let me give you an example, because one of the things that stalls, I'll show you some equations, but if you're looking at vibrations in a structure, okay, then my specific example is going to be on rockets. And so when we are looking at the vibrational mode of a rocket as it's flying through the atmosphere, you have the rocket engine that's generating some fluctuations because it's noisy, right? And you have the aerodynamics around the vehicle that are generating some fluctuations. Then there's a coupling between those two. Rockets wiggling like this, engines wiggling like that. You can have some natural frequency coupling. Rockets are also usually not as infinitely as stiff as you might think. It's true of all aircraft. There's actually some bending modes. And so one of the struggles you have to do is you have to figure out where are these dangerous mode couplings between the engine and the vehicle, and how do you stiffen it up or dampen these modes, because it can literally rattle a rocket apart. Okay. Now the challenge is n cubed per eigenvalue, and so what ends up happening at rocket companies is you have a very reduced order model. Your rocket is basically converted into this like stick and shell, very simple model of maybe 500 points. As in, like, the engine is considered a single mass with a single point that's attached with two sticks to the rest of the vehicle. Why? Because that's 500. That 500 goes into this n, becomes n cubed. And if you're trying to capture, maybe you want to look at the top 20 frequencies. Anyways, the computationally gets really, really crazy. But the result of this is that that's sort of the highest level analysis, or maybe n is 1,000. Don't quote me here. Either way you look at it, it's a very reduced order model of your rocket, and you're trying to use that to understand what are your natural frequencies of the rocket, and it can literally go drive the design into circles. Okay, and so you do this because we have no other way really of doing it. Now you can eventually build a rocket and you can hang it and you can bang it, like you can do that sort of once you build a prototype, but sort of before that. So that's a very real problem. This computation is very crazy. And so all the reduced order methods to get to this are actually pretty brutal. So I'm not going to talk about those reduced order models. We're just going to talk about these sort of eigenvalue solutions. Okay, and so one of the things that you'll see a little bit later in the chapter. I'm going to introduce it here, but usually dynamics are second order differential equations. So you can think of an unvariable y. And I'm going to differentiate it with respect to time. And then, let's see, usually I'll do this, dy dt plus y is equal to some input, okay, b. Now, this is a second order equation. Usually what you'll end up doing is you'll say, hey, I'm going to define this differently. And I'm going to say, I'm going to x1 variable, that the time rate of change of that is x2, and then the time rate of change of x2 is then equal to, and kind of replace it into here. Okay? And so this would be minus a x2 plus b x1. Okay? And so you're going to convert a second order differential equation into a pair of first order differential equations. And then you would kind of go from there. And so if you imagine, right over here, imagine a very simple system, okay, where I have two walls, and then I have a block M1, and I have a block M2, and then between these I have a spring. Okay, so I have three springs, and if you go write the differential equation, mass times acceleration is the forces, and you get all your forces correct. This is the dynamical system that you can cast into differential equations. Now, where does this relate back into eigenvalue? Well, again, you're not solving for, you could solve, I'm going to give it this input, I'm going to drag this mass, and I'm going to push it to the right. And you could either solve for it's the steady state, or if you're going to try and keep it in this form, you have the time dependence, you're solving for the wiggles. The eigenvalue version of this problem, and you can imagine it over here, there's actually two sort of standing modes where if you keep driving it, it'll keep repeating it. So one is actually, I'll draw it like this, where you are wiggling the modes sort of out of phase. So that's this example where I'm grabbing these masses, and if I sort of wiggle like this, if that input it'll kind of build upon itself. This will be kind of a natural frequency. The other one is sort of where they're aligned. Okay, will be sort of a natural frequency here, so kind of the center spring doesn't get engaged that much. So these are the natural frequencies, and a lot of what you get into when you in the world of mechanics and dynamics and vibrations, and again even guitar strings, you really want to understand where are these natural frequencies, because that's where you can have the highest stresses, or the system can go absolutely crazy. Now, what's not modeled in here, because these are just springs, what's not modeled in here is any dampening. Okay, so springs are not perfect springs. There is a little friction here. If these masses are sloshing back and forth in the air, there's a little bit of dampening. And so it's usually okay to do this to find out the natural frequency, but then the Q value is what it's called in dynamics, is actually like, well, how crazy does it get, right? How weird, or how much does your fan shake before it sort of gets past that natural frequency and then settles into its normal operation. So this is, like I said, is a pretty, it's pretty computationally expensive. It's absolutely tied to lots of real physics. And, you know, these eigenvalues, now especially in situations like this where the eigenvalues are tied to time, usually what ends up happening, if your eigenvalue is greater than 0, this is unstable. And so your system is going to exponentially diverge. Okay? If your eigenvalue is less than 0, you have stable. So this might be a system where your system, like whatever your system is, like a spring mass system, or, you know, car vehicle, whatever it is, if it's stable, it'll have some kind of shakes and it'll settle down. And then if you have sort of 0 plus an imaginary form, this is sort of your harmonic. Okay. This is where your system is going to just kind of keep swinging back and forth between a couple different states. Okay. So this is a pretty important step. You can go dig in a little bit more, but really, because I'm trying to focus this as both practical and then the computational part of it. There's something called, just like we did last time, last lecture, we talked about iterative methods. So inverting a matrix was an n cubed operation, and there are iterative methods that make it n squared. There's also an iterative method here that makes this operations n squared times some number a iterations per eigenvalue. And it's called the power method. Power method is the main one. Okay? And effectively what you do, it's pretty simple. Matrix A, you would guess sort of a random seed of x, and then you would hit, you know, A sort of hits it, and then you get that, and then you kind of just keep hitting it again. Whatever this result is, you scale it back down, and that's your new x guess, and you whack it again, new x guess, and you whack it again. Because again, you're actually trying to find this. And so what ends up happening with this power method is if you kind of keep applying A to this guess, eventually what you'll, and you keep rescaling your guess back down to some norm, what you will eventually hone in on by kind of A sort of whacking x a number of times will be this first eigenvalue. So that lets you get that eigenvalue. And then you can come back and you can whack it in a way that's orthogonal to that eigenvalue and get your second one. So these power methods are helpful. Again, like going back to my rocket analogy, you know, we're actually not searching for you know, all of the natural frequencies, all like 10 million natural frequencies, right? You're actually looking for what are the largest ones, okay? In fact, back to this, actually I don't care about the ones that are stable. I'm curious about the ones that are unstable, right? And then related to this, the last thing to kind of talk about here is singular value decomposition. And this is getting, I'd say, more use now. And this is actually taking that matrix A and converting it to a couple matrices. Right? And I'm running out of room, and so I'll just kind of show this in words, and I'll draw it out here. So both U and V here are unitary, which means basically their inverse is equal to their transpose, and there's a complex conjugate in there. So any matrix can decompose into this, and this matrix is a diagonal, has diagonal entries. Okay. And there are algorithms that will solve this. The highest level I'm going to lead you with now, without digging into this algorithm too much, that will solve this. And basically, these diagonal entries are the eigenvalues. Okay, so why is this useful? First, this is actually how image recognition works. It's actually taking that image space, which is, you know, two-dimensional image with all of these colors. It's actually this massive dimensional space. And it's actually solving for these sort of, each eigenvalue, if you will, is sort of the largest energy content, the largest modes. And so a lot of the early image recognition, and now actually a lot of AI is powered with this tool, is actually breaking these images. Again, it's image just a set of unknown, you know, taking all your pixels and vectors and lining it up like this, and then starting to do sort of pattern recognition. This is actually where a lot of it came from. But it's also very powerful from both solving for an eigenvalue and then also inverting it. And really the easiest way to sort of visualize it, and I encourage you to kind of go read in the book. But if you take, I'm going to draw two things here. And so here's two vectors and a sort of a circle of potential fields that are represented by these interactions. And so these interactions, let's say what it does is sort of stretches and rotates these fields, and then these two vectors are no longer orthogonal, but they kind of look like this. Okay. This is a graphical representation. There's a lot of richness in here that I'm just covering in basically a minute. Okay. Well, this is equivalent to V, this thing over here. What actually V is doing is actually keeping the unit circle, but first rotating the vectors. That's V. And then sigma is then, you know, stretching this along its directions. And then U is then rotating this up to that point. Okay, so that was a really, really high level. And so I'll just kind of summarize here. All right, so eigenvalues, AX equals B is our general thing, interactions with stimuli. We're actually, when we're looking for eigenvalues, we're saying, hey, when is the response proportional to the stimuli? The proportionality factors can have a couple of different consequences if this is a real dynamic system, like springs or rocket vibrations. So things that are unstable versus stable versus harmonic. The biggest interaction with vibrations, whether it's guitar string or this rocket, it's actually the natural modes. You're actually most curious about the largest eigenvalues. And so while this is cost n cubed to solve per eigenvalue, you're really just hunting after sort of the largest couple of modes. So there are iterative methods, just like there were in solving the matrix, that you can go decompose it. And there are advanced methods like singular value decomposition where you can get more information out of it, where you can just kind of take this matrix A and you're able to decompose it into things like rotations and stretchings and realignings. And so there's a lot of, but it's just scratching the surface of the math. That's why there's this whole area of the dynamics and eigenvalues, and even getting into things like chaos theory, and then of course AI is now playing in this world. It's really rich. I'm barely just scratching the surface, but the key point here is there are tools available, and don't just do it blindly, because all the same things are true that we've talked about so far, which is, you know, this is a lot of operations. The challenge of discretizing your equations, like I was talking about that rocket, that's one challenge, as well as the digitization and the errors that can be associated with this. So solve wisely and dig in. This is one field where people usually only scratch it, and they're missing a ton of both the difficulties as well as the errors that can crop up in this. So go dig in and read, and we'll see you next time.